Here is a thin film problem called an anti-reflection coating. This is the coatings that are on your glasses and lenses to minimize the amount of white light that reflects. So we have an anti-reflection coating on glass. Glass is index of 1.5, and they're usually made of magnesium fluoride. And the reason is that's very tough and has just about the index that you would want. It's not exactly the index you'd want, but we can't just have any index material. So magnesium fluoride is the closest and the cheapest and the toughest. So its index is 1.38, and they're giving you the thickness of the film, 500 nanometers. So first thing we want to think about is the anti-reflection properties. So what is the longest wavelength for destructive interference on reflection? Now, you may be tempted to memorize a formula for every possible case of air, glass, film, air, film, glass, air, soap, bubble, water, air, but you're better off just going through the diagram every time. So let's go through the diagram. This is an anti-reflection coating. Let's see. We know we're going from air, n equals 1, to the film, which sits on the glass, n equals 1.38, to the glass, n equals 1.5. And we know when we're looking at interference on reflection, it's because some of the light bounces off the top interface. Remember, light reflects at an interface, but it also transmits, and some light bounces off the second interface. And it's the interference of those two that we care about. And we can assume this one is so far away that its reflection is irrelevant, or that it's really small. You're always just doing 2 reflections in this class. Okay, so what we want to know is what is the phase difference between these two? Are they in phase, out of phase, etc.? So we have a formula for that. It is that the change, the difference in phase, is equal to the difference in distance, delta x, difference in the path, over the wavelength in the medium where they have the path difference, times 2 pi, basically how many radians difference is there due to the path difference, plus the delta phi due to reflections. This is how we usually write for light. There could also be difference in phase due to the source phase constant, but they have the same source. So the phi naughts are going to be the same. Okay, so let's look at this and say, well, delta x in this case is just 2 times the film thickness. It goes down and back up. We drew it at an angle just so you could see it, but somewhere the problem will say it's for normal incidence. So that's why there's a 2t there. You may think there's something missing here for light, but I wrote lambda. So lambda technically means the wavelength in the material. We usually do problems in terms of lambda naught. Lambda naught is the wavelength of the light in vacuum or in air. So if in a problem you're told a wavelength, you're told to find a wavelength, you're always referring to what we call the vacuum wavelength. So we have to put the value for lambda in the material, and remember inside of the material n, the wavelength in that material is lambda naught over n. It's just whatever the vacuum wavelength, which really depends on the frequency of the light, is divided by the index. That's why you'll see this formula often with a lambda naught here and n there. That's what's going on. Often people might forget to write the naught there, because we always talk about the vacuum wavelength. We almost never talk about the wavelength in a material. So it's so common, sometimes we forget the naught. All right, so then that's all so we know that, we're looking for that, 2 pi plus, and now we need the difference on the reflections. Okay, so we need to get the reflection shift due to one minus the reflection shift due to the other. So actually we need to think carefully about which one are we subtracting from the other. Well, actually if we put a positive difference here of 2t, that must mean we're subtracting this one, which I'll call 2, from this one, which I'll call 1. Because we're saying the difference is positive. That means the difference must be this longer one minus the shorter one. So really we need the reflection difference of 2 minus the reflection difference of 1. Well, let's see, what are they? So now this is also tricky. Does this one go through a pi phase shift or not? Well, it reflected off of a higher index. It was always in 1, n equals 1, n equals 1, n equals 1, but the bounce was at n equals 1.38. So reflection at a higher index causes a pi phase shift. The other ray transmitted, no pi phase shift, and then it reflected, and it never left 1.38, but it reflected off of 1.5 higher. Also a pi phase shift there. And transmission never causes a phase shift, so there's a pi phase shift there. So actually in this case, this isn't 0. This is pi minus pi, and it has no effect. And there you go. So you get all this, and you say this equals what? So we want it to be destructive, because it's an anti-reflection coating. What's the longest wavelength for destructive interference? So it'll be destructive if it's equal to pi, 3 pi, 5 pi, or 7 pi. So m pi, where m equals 1, 3, 5, 7, like that. All right. So there we set up the whole thing in terms of numbers that we know. We know the thickness, we know the index, we're looking for that. We just got to figure out which m to use, like that. And we were asked, what is the longest wavelength? So you can kind of look at this and see, well, if lambda's down here and m is there, I want to put the smallest number here. The biggest lambda is going to be the smallest number, so I want the smallest number. So, or if you wanted to, you could just find lambda for every one of these and say, oh yeah, this was the smallest. But you can kind of see, since lambda and m are inversely related, and you want the smallest lambda, you probably want the smallest m. So when you do that, when you say m equals 1, and you solve this, you just plug in, I won't do the algebra because my board is not big enough, you get 2760 nanometers. Like that. So that's the answer to the first question. What is the longest wavelength to get destructive? Now, if the picture I show is these things on a camera lens, like an SLR camera lens, you might know that you can't actually see light at 2760 nanometers. That's in the near infrared, or the infrared. So if you can't see that, why would they design it for that? The answer is they didn't. You don't always design an anti-reflection coating where the first order destructive interference is the one you want. Because then, actually, in this case, the film would have to be really thin. Maybe it's hard to manufacture the film really thin. So you can make it thicker as long as one of these is in the place that you want it. So that's the point of the second question. What visible wavelength is destructive? So that means visible wavelengths are, and it tells you this, 400 to 700 nanometers. That's where we care. So there's really not an intuitive way to know immediately. All you really do is you just plug in these different values. 2760 is not in the visible. Well, the next number up is going to be a shorter wavelength. So let's see what that one is, and that one is, and that one is. So we're just plugging in more, and I have the answers here. M equals 2, or M equals 3. I got 460 nanometers. So that's already in, that's already at visible wavelengths. And see, that can't be right. That's a typo. 8, 16, 24. I think it's 8, 6. Okay, well, let me just do it real quick. Sorry. Typo. If we were to simply go from 1 to 3, we would divide that by 3. So let me, off the top of my head, write down the correct answer here and see that lambda for m equals 3, lambda is 920. And divide that by 3, 379, 2, yeah, 920 nanometers. Good, not in the visible yet. So you say, okay, going to 3, it got shorter, but not short enough. Let's go to 5. M equals 5. And what is it there? Then, well, you basically divide that by 5, really, is what you would do. It would be 5, without my notes. Let's see, 5 leaves 2, 26, 5, 2 nanometers. That's in the visible. That's red, between 400 and 700. And if you just wanted to check, you could make sure that m equals 7 is no longer indivisible. I didn't do it here. Right away, you plug it in, you're just going to divide that by 7, and you're going to get 3 for the first digit. 7, 14, 21, and it's going to be 3, 66, and it goes into 60. So it's going to be 390 something, but that's not in the visible either. Too short for the visible, too long for the visible. So the answer is m equals 5 at 552 is the wavelength, and it's the third destructive wavelength, even though it's m equals 5, because they're odd integers. All right, so what's the only visible wavelength? There it is. For that minimal reflection in the visible, how many waves or full cycles does the light go through inside the film? So there's not sort of a quantitative formula to get this. Really what you're doing is you're just thinking about how do we get destructive interference? What's happening? We know what's happening is that these are coming out of phase. right? This came out up, this came out down. It's not due to any reflection differences. They both went through a pi phase shift. So the reason must be that for the longest wavelength, this just happened to be a half a wave, right? That's this definition. When n equals 1, that's half a wave. For n equals 3, it must be it went through a full cycle and a half a wave. So 1.5 cycles. And then n equals 5 means 2 cycles and a half a wave. Right? So the answer is 2.5. 2.5 cycles. Because that's what the third time it's a minimum would represent. This is a little bit of a realistic view of these anti-reflection coatings. Notice it only works at this wavelength, but if you plot the reflection, it's centered usually in the middle of the visible. That way it also sort of blocks the reflection of most of the visible. But a little bit of red and a little bit of blue gets through, and that's why you see a little bit of purple often on a cheap anti-reflection coating. I'm sorry, this isn't red, this is sort of yellow-green. Yeah. Earlier I said that was red, that's not red. I was thinking of 650.